Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. Today's screencast, as with most of my screencasts, will be about the reciprocal system, specifically the Microcosmos database graphing facility. You can see here in the left panel the main menu for the Microcosmos database, and here on the right panel you can see the Macrocosmos database. I've already covered all of these layouts in previous screencasts, so be sure to watch those videos. And I've covered all of these layouts in the Microcosmos database already, so let's go right to the graphs. And we'll stick with iron. We'll take a look at water later. Okay, let's go through the fields on this screen. So here's the element compound mix. You can choose any element or compound or mix you want. And then all this stuff comes up. The iron is the description here, form number 1. And then we have solid or fluid descriptions here. So atomic molecular weight. So all this comes up from the previous layouts, so you can see for yourself. Melting temperature in Kelvin, thermal factors, and compressibility factors are here. If this were a fluid, and we'll look at water in a moment, you would see atomic molecular weight, the critical temperature in Kelvin, and critical pressure in atmospheres. Okay, so the graph title is here. This is iron molecular density, and you got to choose solid, liquid, vapor, or gas. Okay, so those are the choices here. So just click there. See, this is a solid, so you choose that. And then the abscissa is going to be the temperature in Kelvin or the pressure in atmospheres times 10 to the 6, or the ionization stage 1 to Z. Z is atomic number. And then here for the abscissa, you put in the low value, which is 0, in this case, 425, in this case, for the high value, the step value, and the 0 tolerance. Okay? And then since we're doing this by temperature, then you got to fix the pressure. So pressure in atmospheres times 10 to the 9th. So this is just one atmosphere, okay? 0.00001. 1 times 10 to the minus 6 is times 10 to the 6 will be 1 atmosphere, okay? And that's for temperature graph. So that's what you would normally use, unless you're doing something involving both pressure and temperature. Now, if you're doing a pressure graph, then you have to fix the T, and you put that here. Okay, now, the graph data will come, the program will calculate the graph data, and then you can actually save that to a file if you want to. Type the file name here, and we'll go there. Now, the key thing are the ordinates. Now, let's look at the possible choices. Now, look, quantum mechanics, no other theory can do any of this. So here we have, let's go all the way to the top here. Aggregate enthalpy in cal per mole. Aggregate enthalpy in cal per gram. Molecular enthalpy in cal per mole. Molecular enthalpy in cal per gram. So we have both that on the aggregate level, which takes into account probabilities versus the molecular. And we have aggregate entropy in cal per mole K, cal per gram K, molecular entropy in cal per mole K, and cal per gram K. We have aggregate specific heat, C sub P, cal per mole K, aggregate specific heat, C sub P, cal per gram K. That's, of course, constant pressure. Molecular specific heat, Cp, cal per mole K, molecular specific heat, Cp, cal per gram K. And now we go, the same thing we have for a constant volume process, okay, both aggregate and molecular. There is a difference between just looking at a single molecule or atom versus looking at a bulk material. Aggregate unit cell volume, 10 to the minus 24 centimeter cubed. Molecular unit cell volume, 10 to the minus 24 centimeter cubed. We have aggregate density here, molecular density. That's what we're doing in this particular graph. Then we have aggregate internal energy, cal per mole. cal per gram. Molecular internal energy in cal per mole and cal per gram. Aggregate cohesive energy in kilojoule per mole. Molecular cohesive energy kilojoule per mole. Aggregate ratio volume to the baseline is 0 temperature and pressure. Molecular ratio of volume to volume 0, that's at 0 temperature and pressure. Aggregate coefficient volume expansion rate times 10 up to the minus 6. And then ditto for the molecular coefficient volume expansion rate. Oh, I went down too far. Okay, let's come back. We've got, let's go back up a little bit here. Okay, we just did those two. Aggregate thermal power in mu volts per Kelvin, molecular thermal power, molecular electrical resistivity centimeters times 10 to the that's minus 6. Thermal resistivity in Kelvin, centimeter per watt. Molecular electrical conductivity, centimeters up to the minus 1 power, and molecular thermal conductivity, watt per Kelvin centimeter. Can I expand that now? We don't want to do that. Let's just let's get back to molecular density. I like that. I'll keep this the same. Right here. And let's keep going down the list. Now again, you won't find any of these in any other theory of the universe. You just won't. We got resistivity, so we did all those. Aggregate Lorentz number and molecular Lorentz number. And those are the units. Aggregate aggregate thermoelectric figure of merit times 10 to the minus 3, and just a regular figure of merit. So look at this. We still have aggregate Peltier coefficient in millivolts, molecular Peltier coefficient in millivolts, aggregate Thomson coefficient, and molecular Thomson coefficient, again, both mu volts per Kelvin. Individual ionization energies, theoretical, best fit, and total ionization energies. That's a sum to get up to a certain level. Aggregate specific heat CP, molecular specific heat joule per mole K. Oh, darn, we gotta go back. Let's see. Aggregate specific heat, molecular, these are but different units than the ones above. Joule per mole K. Aggregate enthalpy, joule per mole, molecular enthalpy. So these are just all the joule per moles. And then we come down to here, atomic distance in angstroms, compressibility, atmospheres times 10 up to the 6th to the minus 1 power. Bulk modulus, atmosphere times 10 to the 6, modulus of elasticity, G. That's E and G. Those are the common symbols. Average index of refraction, edge A, edge B, edge C can be different in the cell. The index of refraction can be different. And then finally we have sound speed, longitudinal rod, meters per second, longitudinal bulk, whatever that is, and transverse bulk. Solid. All right. So I'm going to keep the molecular density. If this were, well, we'll do the fluid ones later. So basically, you would just click here, generate the graph data. It'll take a few moments, and it'll put it, all the stuff right here. Okay. So the graph disappears. Now you can these are the commands for the graph. Ordinarily, you don't have to change any of these, okay? If you wanted to add a regression, if it's available, you can add the regression function to the graph. So the default command should ordinarily work, but I'll just scroll down. So look at all the choices you have. You can make it as pretty as you want. And then you click here, and there's the graph. So this is the molecular density, and as you would expect, it goes right down just like that with temperature Kelvin. Okay, now let's look at water. We'll just do one more. And this one is gas density. So this time I have the fluid parameters here: critical temperature, critical pressure. It's G for gas. So this will be temperature Kelvin, just like that. A low value, high value, step value, zero tolerance. The fixed P, so this time this is under pressure, okay, because the one is there instead of at the end. And, okay, so this is temperature. Now for the fluid ones, we got aggregate enthalpy, molecular enthalpy, aggregate entropy, molecular entropy, specific heat, molecular specific heat at constant pressure, specific heat, constant volume. I'm not going to read all these, but aggregate molecular density, internal energy, aggregate and molecular. I mean, you're not going to find this in quantum mechanics. It's impossible. The reciprocal system completely and utterly supersedes every other theory. Coefficient of volume, expansion, thermal power, electrical and thermal resistivities, Lorentz numbers, aggregate thermoelectric figure of merit, Thomson coefficient, invisible, ionization energies in total. And then we have the joule per mole K for aggregate molecular specific heat at constant pressure. And just scrolling down here, it's the usual stuff. Okay. Now which one are we doing? We want to do gas. We don't want to do sound speed. I want to do gas density. So let's see what we got. Do we want aggregate or do we want molecular? I guess we could try molecular. Okay. Invert the field. So it doesn't like that, so that's a good trap. Oh, I see what's going on. I see, that's irrelevant, because we're doing G, we got to go down here, which is right, gas density, that's correct. Okay. This is only for solids, this is for fluids, including liquid, vapor, and gas, all right? So here we're going from 647.13 here to 1227 here. Step value of 10. And let's regenerate the data. Okay, it's been regenerated. You see the temperatures were first, and then the density. Okay, and generate the graph. So there's the graph. So as you would expect, with increasing temperature, it's almost a straight line down. For the gas density of water, steam actually. Again, you can change the the title style, and axis of labels and all that stuff down here, but it's really not necessary. All right, well, we covered a lot today. So you can just see that the reciprocal system is now fully computational. So now I've covered this entire Microcosmos database. I've already covered solid matter properties, interatomic distance, valence, specific heat, energy, and entropy, thermal expansion, compressibility, electrical and magnetic properties, isotopes, and atomic spectra. I've also covered in previous screencasts liquid vapor. I gotta shut this off. Okay, I've covered liquid vapor, gas matter properties, volume and density, specific heat, energy and entropy, viscosity and surface tension, and electrical and thermal conductivity. I've also covered cosmic elements and material and cosmic subatomic particles and photon properties, and today we covered graphs. But not only do I have a microcosmos database, I have a macrocosmos database, and in previous screencasts I've covered all of these astronomical properties, the universe as a whole, galaxy clusters and groups, galaxies, star clusters, stars, planets, moons, minor bodies, nebulae, gas and dust, and voids. If you want to just jump to pictures and videos, you click on events. And I've covered the graphing function for the macrocosmos database here, general progression versus gravitation graphs and star graphs. That's the properties of stars from surface to the core. Now this may be kind of advanced for some of you, but if you want the simplest possible treatment, please obtain my work, The Unmysterious Universe. It's still in print, published decades ago. It's gotten a great many good reviews on Amazon. It's only $9.50. It'll give you the basics of the theory. Then, if you do want all the math and all the detail, then please get my magnum opus, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. 711 pages in the PDF file and 711 slides in the PowerPoint file. It contains thousands and thousands of equations, has numerous tables, figures, graphs, everything. It'll keep you busy for months. Then when you're finished with that, you're in good shape to get these two database modules, the Microcosmos database and the Macrocosmos database. Now my theoretical physics mentor, Dewey B. Larson, was also a theoretical economist, and I've made his work in economics also fully computational. That's my software program called Optimal Economist, an implementation of Larsonian econophysics. Covers the microeconomics of individuals and businesses and business sectors, and the macroeconomics of whole countries and regions. Completely and totally supersedes Keynesian economics, just as the reciprocal system totally supersedes most of modern theoretical physics. All right, that wraps it up for today. As usual, I ask that you study the reciprocal system carefully and prove it for yourself. And thanks for your attention.